first part of the afternoon, we wanted to cover one-sided communication in MPI. This is in many ways, is another programming model. So I like to call MPI a programming system. Message passing is a programming model. MPI is a system that includes message passing. It also includes one-sided or remote memory access programming. And the basic idea here is that you can expose parts of the memory and do direct copies or operations into or from remote memory. So in two-sided message passing, one process sends, another process receives. In one-sided, one process decides the totality, the completeness of the memory motion. So for example, it might decide I'm going to take some data from my memory and put it into some other process's memory. So I may decide that I have some memory that's accessible to other processes and some memory that's not. And I may decide to have some data move, for example, I may define some address space that's available to everybody and have operations where, for example, I might put from some memory location, it might be my private memory location. This is the case is a put in from process zeros to process two's public memory region. I might do a get. So get, I have to somehow cause data to come from process one over here, or I might do something else here. I might do, this could also be a get, or I could get data, do an update here, and have returned the data that I got. And so again, sort of looking at it this way, in the two-sided, you have to you explicitly send data, and the target process has to explicitly say how it wants to receive it and where that data is going to go. There are good things about that. In particular, in each program, I can identify where in the code these data updates happen. So this is one of the reasons why the message passing code is sometimes much easier to debug than one-sided code, because it may be hard to figure out all those communication patterns, but that pattern of how data is moving is explicitly exposed in the code. Yeah, so that's a good and a bad thing. In the one-sided case, I just put, and the data arrives over at process one, possibly without that process doing anything else. So as I'm looking at my code, there's no way for me to say, before then, that data is undefined. After this moment, I know that the data has been updated. At the same time, it means that anything that's going on here, in terms of, say, if there's a delay, if process 0 takes longer to get to the point where it's putting this data, that doesn't affect process 1 because it's not synchronized with it. So here, if process 1 is waiting to receive data, if process 0 is late to the send, then process 1 will just be waiting around for that send to happen. And so the one-sided communication helps decouple the data movement from the synchronization. In two-sided message passing, those things are connected together. And anytime I'm sending from one, receiving another, I am both communicating the data, but also synchronizing that the receive has to happen after the send. In one-sided, I separate those things out. Now, it does leave open that question of how does, in case I'm doing this put here, what if process 1 needs that data? How does it know? So we'll talk about that in a little bit. But a key, again, is that in the one-sided case, I separate out the description of how data is moved from how I decide that that movement has been completed. Okay. So in particular, one of the things I can do is I can do multiple data moves and then use a single operation to indicate completion, to signal that the data has been appropriately moved. Additionally, as Pavan talked about yesterday, in some cases, the hardware can perform these moves without any involvement from the processor. So in particular, because I'm, say, just doing a put or maybe just doing a get, I don't need to go and find, say, a matching tag, a matching context ID. So I don't need to do tag matching or envelope matching. And so in some sense, you can think of it as the process of deciding where I'm going to put that data. So one process says, I'm going to put this data at that specific location in memory. In some sense, that matching, that decision of where does that data go has already been determined and somehow communicated to the process that's doing the put. There are some things that are easier to express. In one-sided, it's sometimes the case that the process that has the data to send it knows where the data needs to go, but the process that's receiving it might not know where the data is coming from. And so in this case, a one-sided model can work better. And again, advanced hardware for networks that supports some of the one-sided operations can be much faster. And these operations can include more than just put and get. So even InfiniBand has a small set of atomic update operations that can be used by an implementation that's aggressive enough at taking advantage of that. I mentioned also can be really useful for these dynamic cases where one process knows what data needs to be communicated and to where that data needs to go, and rather than needing to communicate that information to another process for it to then post the appropriate receive, you can just deliver it. This makes sense in the cases where you have created some distributed data structure and you can sort of initialize it so that all the processes understand it, then they can do the updates together. And we'll see that MPI is organized in that way to think about this as a distributed global data structure. And global here, as pretty much everywhere else in MPI, means with respect to some communicator. So it does not have to be COM world. It could be any subset communicator. OK. So if we're going to use the RMA, what do we need to know? How do we do this? So we need 4 things. We need to understand how to create that notion of the public memory. Essentially, how do we specify to other processes that this part of memory is accessible to them? We might want to expose all of memory, but it's actually more common to say that there's only this distributed data structure that needs to be accessible to the other processes. Okay, so once we've done that, I'll cover how we do the communication. How do we do reads and writes and updates? And I will say MPI 2 introduced a fairly limited set of operations. It was sufficient to do some applications, and there were a few implementations, particularly on the Japanese supercomputers, that took advantage of this. MPI 3 has a much richer set of one-sided operations, and I think makes it much more interesting as a programming approach. And one part of that takes advantage of this one-sided model to apply it to using shared memory within the node. You may have heard of this described as the programming model MPI plus MPI, as opposed to, say, MPI plus OpenMP. And I'll say a teeny bit about that today. Next, as I mentioned, if I'm moving data, particularly if I'm moving data in a one-sided way, so I'm putting data someplace else, how do I know first when my put has succeeded, but much more interestingly, and maybe much more important for a correct program, how does the target of that put know when the data is available? And so we'll talk a little bit about the data synchronization. Then finally, a little bit about what we call a memory model. So once we start talking about shared memory, there are all sorts of subtleties that come up. And we have to really talk about what it is we mean for memory to be updated, memory to be visible after one of these one-sided updates. Okay, so in principle, any memory that you create it's just visible in that process. So if you've got multiple threads, they can all see it, but no other process can see it. There are, of course, ways to, there are OS-dependent ways to get access to it, but pretty much think of the programming model. The programming model that C and Fortran expect is that memory that you've created is only accessible by that process. So to make that memory accessible even to the MPI RMA operations, the one-sided operations, you have to create what we call a window object, or a window, which consists of the locations in memory from each process that will be available for operations on that window. And that window is the one-sided counterpart of a communicator. So as we'll see, just as all sends and receives are with respect to a communicator, and with different communicators, you indicate different groups of processes. For the one-sided operations, everything is with respect to a MPI window object. And so once you've got this object, then you can do all the operations. And so again, think of it like this. These yellow squares represent the entire memory space of the process. The gray squares, and we sort of drew this to make it look prettier, but a memory region is a contiguous block of memory. So it's not like a subarray out of this. It's a contiguous block of memory. But they might be different sizes, and they might be at different locations in each of the processes. They don't have to be at the same virtual address. And the window object consists of all of those memory regions that each process has made available. And then I can do things like a get operation. So in this case, process 0 has done a get. It can only do a get from the exposed memory, but the result can come back anywhere it wants. So here I have it coming back to the private memory. It could, in fact, come back to the public memory. Let's see. A put, sort of the reverse. It can start anywhere, but it will end up someplace in that exposed memory. Okay. So in MPI 2, the set of one-sided interfaces we had was pretty much this for creating the windows and moving the data. So you would call MPI win create. You'd give it the memory region that's going to be your public region, and a communicator. This is a collective call over that communicator, and a little bit of other information, and it will give you back this window object. As is typical with MPI, then you use MPI win free to free up that object, just as you would use MPI com free. And then there was MPI put, get, and accumulate. Accumulate is the remote update, so it's sort of like a put with an operation. In fact, it very much looks like that. All of these operations are non-blocking. So I had argued for calling them I put and I get and I accumulate because they act like that. I lost that, and then I read a paper that was published that got through the reviewers where the paper had done timings as if these were blocking. So just word to the wise, these are all of the RMA routines are non-blocking. Okay. Now, that still doesn't give us everything we need. I will talk a little bit about the synchronization. How do I, it's non-blocking. How do I know when it's complete? Right. So I haven't set out to do that yet. We'll get to that later. In MPI 3, we added 3 additional ways to create a window object. So we had the MPI win create. MPI win allocate is like MPI win create, except instead of you providing it with the memory region that you want to expose, you just tell it how big that region is, and it gives you back the address of that region. Well, it actually gives you back the window object, and you get back the address of that region. Another thing that people wanted to do was say, well, I'd like to use this RMA stuff, but I don't know where all the data is when I would create the window. So I have some sort of dynamic data structure that I'm using, and I'm going to create in free memory. So there's a different kind of window object that essentially gives you a window object with no memory attached to it, but allows you to attach memory to it as a local operation in the MPI sense. What that means is it's not collective. Any process can call the routine to attach memory to the window object, and it doesn't have to synchronize that so that all the processes are calling it. So you can allocate some memory and say, then attach this to this window. And then there's a fourth type, which we're not really going to discuss today, but I want you to keep this in mind because it's the thing that enables the MPI plus MPI, which is it's like MPI when allocate, except what it gives you is memory that is shared among the processes, in the sense that instead of using the MPI routines to put and get to it, you can use the available routines in the language to load and store from it. So basically, you can get a pointer to it, and then you can store to it, and other processes can use the pointer that they got and read from it. Now, the pointers might not have the same may not have the same addresses because they're virtual addresses, but it would be the same memory, and an update that's made by one process will be visible to another process. Okay, so this is what when create looks like. And so we pass in the memory, the size in terms of an int. We pass in a displacement unit. And that's essentially a way to say, how am I going to indicate where in that memory I'm referring to something? So you can make the displacement unit 1, in which case all of your locations are going to be offsets in bytes from the beginning. But you could also use, for example, the size of an int or size of a double, in which case your offsets are all going to be in units of doubles. So for example, if what you're doing is exposing an array of doubles, if the displacement is the size of a double, then when we get to the communication routines and you see the offset, an offset of 3 will mean go to the third, let me say the third, so 0, 1, 2, 3. The third double from the beginning of the window. 0th, 1st, 2nd, 3rd. Right? Okay. You also pass, again, it's collective over a communicator. So that could be ComWorld, it could be something else. And you get back this window object, just like from MPI ComCreate, you would get back a communicator. Info, how many people know about MPI info? OK, so just a couple of you. This was something else added in MPI 2. It's essentially it's a key value bag that's used to pass miscellaneous data to some of the MPI routines. It's used for the dynamic processes, which few people use, although there are a couple places. It's used for the I/O interface, so for MPI files, and there's a couple other places you see it. But one of the big uses is for RMA. It allows you to pass additional information where, for example, you can, the user can say something about how they are using the one-sided, and that can allow the implementation to optimize for it. And as a sort of general key value bag, you can use it. It's very extensible. It can be used to pass all sorts of information. It is one of the few examples of where it is valid to pass a null handle to an MPI routine. So in many cases, using a null handle is an error. In this case, using MPI info null is a correct way to say, I don't have any extra information for you. So again, it's pretty simple. I allocate some memory here. I just use it anyway. I pass the address, the size in bytes, the displacement. I'm going to be using this as an array of ints, indexed by ints. MPI info null, I don't have anything else to say. It's over com world, and I get back a win. And I can use this, and when I'm done with this window object, I do an MPI win free. Just like com free, I pass the address of the handle. The handle will be set to MPI win null. Yes?
I don't know if this is a dumb question at this point or not, but I'm curious. What I don't understand is, are these windows identical? Is it a single window that all processors share, so that if they, if process 0 makes it, they all see the same memory space, or?
So what they, let me go back. What each process has done is said, here is some memory. So in that example, each process allocated a block of memory. So that memory is different. So each of them has its own, there was that A equals malloc of 1,000 times size of int. So here's 1,000, here's 1,000. We'll say this is 1,000, and this is 1,000 words. But they could have been different. So for example, process 0 could have allocated 1,000 words for A, and the other processes could have said A is the null pointer, and the length of data I'm going to provide is of size 0. Then I call win create collective over that communicator. And so what do I have at the end of that? Well, so I don't have shared memory. What I have is a win object, MPI win object, which is like a communicator, which will allow me to use a special set of routines, MPI win, put, get, accumulate, and some other ones, to access from any process the memory on any other process that they gave. So, we'll see an example of that. But what this is doing with the MPI win create, MPI win allocate, MPI win create dynamic, is it provides a way for each process to say, I have some private memory, and I'm going to make that private memory available to other processes through these one-sided communication operations, through these put, gets, and accumulates, and variations of that. It's only in the case of the win create shared that I get back actual real-life shared memory. Okay, so the rest of these are just a way to say, here's a piece of private memory that is just regular process memory that normally I would just be doing send receives to, that I'm going to make it possible to communicate with that memory in a one-sided way. Okay, so
is there two copies of data in private and shared?
Let's defer that till I get to the memory model part. So maybe right now, just sort of think of it as there's this yellow memory, which is your entire address space, and you did that A equals malloc of 1,000 times size of int, and that gave you a block. It's still in your regular memory space, but it's a special part that you've given to the win create. So the other processes know about, so the other processes know that process 3 provided this block of memory. Win allocate is pretty much the same thing, except I don't give it a pointer. I get back a pointer following the sort of C idiom. This really is a void star star pointer, but that doesn't work right in C, so it's declared as a void star pointer, but it semantically acts as a address of a pointer of arbitrary type. That's what it is. And so you just say how much I want, what the displacement unit is, the same info, the same the communicator, what are the processes, and you get back the address of the data and the window object that you get to use. And again, it sort of looks like this. So instead of doing a equals malloc of 1,000 times size of int, I just say I want 1,000 times size of int, and I get back a. Okay. And then, as I mentioned, with create dynamic, this is used when what I'm going to do is during the course of the execution of the program, I'm going to discover that I have memory that I want to make accessible through this method to other processes. So say, for example, I'm doing an adaptive mesh refinement code, and some process creates a new mesh, but wants to make that accessible to the other processes. Well, what it can do is it can create a dynamic window like this and attach that memory to the window. Now, that's not going to be enough because no one else knows that I've attached the memory. So I'll have to let the other processes know somehow that that memory is there. But once I do, they'll be able to access it. And so this is what this looks like. So in this case, I create that. I have even fewer arguments. So basically just have the info argument. And again, I can say no special information. The communicator, in this case, all of the processes in COM world, and I get back the window object. So there's no memory associated with it yet, but to mimic the same sort of creation that I've done in the other two, here I would do a equals malloc of 1,000 size of int, and then I can use MPI when attach, take as input a window that was created with create dynamic, and pass it the pointer and the size. And now other processes, if they knew about it, could do puts and gets to it. And I have not said how they would find out. And eventually I could remove it with MPI when detach and then free the window. So those are the 3 of the 4 ways to create these window objects. As I mentioned, except for MPI when create was the only one that was in MPI 2. These others were added to MPI 3 to generalize the model. Next, so we made the data available, but we still haven't communicated. So there are a number of routines, and there's some variations on these. The first 3 were part of MPI 2. So just get, put, accumulate. We've already seen those. In addition, there's a get accumulate that was added in MPI 3, a compare and swap, and a fetch and op. And so get, it basically has to do everything that you do with both send and receive. It has to provide all the information you'd have with send in terms of where is the data, how is it laid out. So one of the things about the MPI routines for one-sided is that they take data types. So we have this data type here. So I've got the origin address, the origin count, the origin data type. So that's the address of the buffer on the origin process. That's the process that is calling the RMA routine. So in this case, it says origin, but that's where the data is going to land. The target, it indicates, so the target rank is which process am I going after? And that rank is with respect to the group of the communicator with which I created the window object. Then the displacement, so that's essentially the index into that memory relative to the displacement unit. Okay, so if this is 1 and the displacement unit was 4, then that would be 4 bytes from the beginning. So if the size of int was 4, that would be the sort of 0th first int in C indexing. Count and data type is just what it is for a send or a receive. So this many instances of this data type, and then the win with which this is respect to. Just like I would in a send or receive, I would have included a communicator. And so that's going to get data from the memory that was made accessible back into this origin. And that this displacement is relative to the beginning of the memory that was exposed by the win create or the win allocate. And so it's not an address. In the case of win create dynamic, it basically is an address because with create dynamic, you're adding memory at all sorts of random locations. The only way to essentially describe that is with the address. Put is just the reverse, but again, it has the same sort of argument. So you describe the memory on the origin process, the process that is making the call, and then where the data is going to go on the target process. So we got a target rank, displacement, where in that memory region, and then the count and data type. And accumulate is like put, but instead of just putting down the data, it performs an MPI op on it, except only predefined MPI ops. And the reason for this is because, well, it would really be great if you could just define your own operation and then run it on another process. But nobody really wanted, or none of the hardware people wanted us to do that. And so these are limited to the predefined operations, so like sum and so forth. And there are two additional operations. An important one is MPI replace, which basically gives you a different kind of put. But that different kind of put has slightly different atomicity properties in terms of how the updates happen, which is sometimes important. There's also a no-op, which is what it sounds like, is an accumulate that doesn't do anything. Right. And then MPI3 added the sort of reverse, which is a get accumulate. So accumulate is like a put with an operation. Get accumulate is like a get, but with an operation. Again, only the predefined operations. And you get the original data, then perform the update. We're doing, why are we doing parallel programming? It's for performance. There are a lot of subtle issues with ordering. So remember, all of these operations are non-blocking. If I do two puts to the same location, I could define what that means, but enforcing that in the hardware can be expensive. In fact, one of the criticisms of the MPI2 one-sided was that it specified too much in terms of what happens when you did operations that might overlap. So for example, one of the things it said was that that was erroneous, which meant it was an error. It turns out that for a lot of the other programming models that use one-sided, they were much happier if you simply say that it's garbage. Right? That it's not an error, it just has undefined behavior. That's a different statement. And that's actually closer to what most of the hardware does. In other words, the hardware just does something, but doesn't generate an error message. Right? So you would like to stay away from that. And so in MPI terms, that program in MPI2 that was erroneous, in MPI3, it has undefined result if you put to overlapping regions. And usually, putting to overlapping regions is an error. But sometimes it's not. And that's what accumulate is for. So accumulate allows you, for example, say I wanted to add one to a counter someplace, and I wanted to allow multiple processes to add one, I can use accumulate. And I'm expecting them to overlap. That's the whole point. And so accumulates are defined so that the overlapping operations are valid. Now that might require the hardware to do something different. It might be a little slower. But it has that sort of well-defined action. And so that's why there's an MPI replace. It actually gives you a put that has defined behavior. And what it means is I'm still not telling you, for example, if I'm putting 100 words, I'm not telling you which order the 100 words got dropped. What I'm telling you is that in each word, I'm going to get all of one of those accumulates or the other. I'm not going to get a byte from one and a different byte from a different one. So it gives me an element-wise atomic put. Further, also as a change, the accumulates are ordered by default. So I've got multiple accumulates coming from the same process. They will be applied in the order in which they were issued. That's actually harder for the hardware than you might think, because different messages, for example, might be routed in different ways. They may arrive at different times. You actually have to work harder to ensure that ordering. And so one of the things that you can use that info parameter for is to say, honestly, I don't care about the ordering. And we did that because it turns out some people depended on the ordering, and when they didn't get it, their program gave the wrong results, maybe only slightly wrong, which is sort of the worst case. Is like you got an answer that looks good, but it's off by 10%. It's a terrible thing to happen. And so the choice here was the default behavior is correct, but maybe slow, but there's a way to make it fast. And so if you really don't care about ordering, you can tell the implementation to take advantage of that. Doesn't mean the implementation will listen, but it does mean that you can express it accurately in your program. There are additional atomic operations. There's a compare and swap. So compare and swap can be really useful in building certain kinds of data structure updates. There's an example in both our book using advanced MPI, and that example is based on one in the standard that shows how to do a list insert for a list that is distributed among a bunch of processes. And you can use a compare and swap to implement that. Amusingly enough, turns out that just fetch and add was incredibly difficult to implement with the MPI2 RMA. I did produce a way to do that that was reasonably scalable that you can find in the old Using MPI2 book, but that was way harder than it should have been. And so we have, get accumulate actually gives you one of those things, but if you're only doing a single word, you don't need all of those arguments. And so fetch and op gives you a way to do essentially single word get accumulate that we hope will provide better performance. Okay, so create windows, perform communication operations. You still don't know when you can use the data. So we have to talk a little bit about how you know that the data is available and when you can get to it. And there are a number of different ways to do this that depend on the way you're accessing your distributed data structure, and they have pros and cons. And we sort of talk about these in terms of epochs, and we may split the epochs into an access epoch and an exposure epoch. So when is the data exposed and when is the data accessed? And there are roughly 3 kinds of epochs. So 2 of these are called active target. And by that, the data synchronization involves all of the processes. So everybody is active in managing the synchronization. And so the synchronization part actually looks a little bit more like a 2-sided process, because while processes may have specified the data communication in a one-sided way, so just do the puts or gets or whatever, when it comes time to synchronize the data, everybody's participating. Okay? But there's another one called passive target, which is very much more like the truly one-sided, where only the process that's performing the one-sided communication is also involved in doing the synchronization. And that's done with a thing called lock and unlock. There's also a way to cause updates to happen in the middle of some of these processes. Again, with things added in MPI 3, there's an MPI win flush and an MPI win flush all. So let me quickly cover the three of these. In many ways, the simplest one is fence. This is a collective call across all the processes in the communicator that set up the window. And what it does is essentially completes the previous epoch and starts the next one. And so typical use is like this. I do a fence, then I do some RMA operations. In this case, say one process does a get, and it does, then all the processes in the window do a fence. One of the places, thank you. One of the places where this model is very appropriate is with our Halo exchange. So what you would do is you do a fence, you do a bunch of puts for the Halo exchange, you then do another fence, and at the end of that fence, the processes that did the put know that that non-blocking operation has completed. So it means that they can now reuse that buffer or do something else with it. And they know that all the processes that were targeting them, that were doing puts, have also completed, which means if they need that data, it's now accessible. So it's in many ways, it's a very simple model. With the right sort of hardware support, it can be really fast. So some systems have had hardware support for what is essentially a kind of barrier. So I mentioned in the morning machines with fast barriers. So you might have a barrier that makes sure that all of these one-sided communications have completed, and the data is visible in memory, and then returns. So nice, fairly simple model. There's a variation of this that was defined in MPI 2 that is called the scalable communication version. So say you don't have a real fast barrier. And the barrier is going to take, say, log p operations, or the fence is going to take log p operations to affect the barrier. This approach allows each process to specify the processes to whom it is communicating, the processes from which it's expecting data, but doesn't have to say where the data is going to go. So it's sort of a smaller form of doing a receive. It's like I'm receiving data from somebody, but I don't even know where it's going to go, except it's going to go in this region of window that I made available. So this is called post-start complete wait. So you post your region for communication, you start your own communications, you do stuff, you complete your own, and you wait for other things to finish. So like fence, the processes have to, normally everybody calls it post-start and then complete wait at the end. So you bracket the RMA operations this way. The third type, the one that only requires the process that is performing the operations to call it, is called passive target, because the target process doesn't have to do anything, it's passive. And it's called lock and unlock. In MPI, every time we have given something the wrong name in a way that is misleading. And in MPI 2, it was this guy here, because these are not locks, they are not mutexes. These are really a sort of begin and end of an RMA operation. So in particular, you cannot use this as a mutex. What it does, again, is allows you to say, think of this as, I'm going to begin some RMA operations, I issue my RMA operations, and then I wait for them to complete. So this is, lock is I'm about to start, unlock is I need them all to finish before this returns. Okay. And so when that returns, what I know is that the buffers that I specified for these non-blocking routines can now be reused. Right. So you might say, well, say I had done a put here over to the target process. How would the target process know that its data was available? It doesn't. Right. There's no notification that the data is available. It has to do something different in order to access it. Now, one of the things it could do is it could do a lock and then access its own memory. And what that will do is ensure that it gets the memory, the update either before or after this happened. OK. So what do those look like? The routines look like this. So I lock with respect to a particular rank. There's a lock type. There's a shared and exclusive. So you can say it's OK for other RMA routines to act on the target process at the same time. So for example, say I'm doing an accumulate for that one counter. I might be expecting other processes to be able to access it at the same time. Or I say exclusive, in which case this will ensure that whatever RMA operations that I specify will happen exclusively as a block with respect to the other processes. But it still doesn't say that this lock operation is not a mutex. There's nothing that says that this won't return until I have exclusive access to the window. And then unlock is the way you end that set of accesses. This assert is used to provide some information that, again, can be used to optimize. You might say, well, why not use an MPI info? Well, why do you think we didn't use an MPI info there? Yes, overhead. So for when create, that's a rare operation. So passing it key value pairs makes perfect sense. This operation, if I want to update a single word, if I want to do that counter thing, how do I do that? I do lock, accumulate, unlock. So if I'm doing a lot of those, I don't want to be spending a bunch of time reading through a key value pair list for stuff. Right? So that as a compromise, we have an assert that is just an int, and a 0 is a fine assert, which says I have nothing to tell you. So it's sort of the counterpart of MPI info null. OK, so there are issues with this. So when should you use the RMA? So you can use the RMA when you're facing overheads from tag matching, buffering, and so forth. You can organize the code to do one-sided operations in a way that's not too complex. Then you can get the benefit of doing these operations directly. In addition, on systems that have the right kind of network hardware, it may be much easier for the implementation to give the data transfer over to the network hardware and say, just move this data, because it doesn't have to worry about doing any sort of tag matching at the destination. Essentially, it's given, if you're doing a put of a contiguous block of data to a window, it's possible to compute the location in memory where that goes. The network hardware can just send it. The passive mode gives you, additional benefits, but it also requires the MPI implementation to handle the sort of passive operations access. So it means that the MPI implementation has to be able to deal with, for example, an accumulate to remote data. That sometimes can be done in hardware, but sometimes will require the CPU to get involved, which means that the CPU will have to know that it needs to get involved. And that often requires setting up a separate agent, often a separate thread, to process some MPI messages. And that separate thread is going to consume some resources. So there's a trade-off in an MPI implementation between the ability to make good progress on these operations and the ability to provide the maximum computing horsepower for your application. It can be worth it if your application is dynamic enough. So particularly as there are more and more cores on a node, burning up part of one core in order to provide this progress to provide more dynamic communication can be beneficial. Also, if your application is set up so that it's more flexible in terms of how it manages its work internally to a node, again, taking up some of a core to manage that progress can be useful. You can also use this, for example, to do shared arrays. There's an entire programming system built on abstraction of global arrays that the MPI3 RMA, but not the MPI2 RMA, can essentially replicate. In fact, one of the current implementations is now really done in terms of the MPI3 RMA. And so can give you a very nice model, particularly if you have accesses to data that are really driven by the needs of the process that needs the data, as opposed to the coordinated efforts between pairs of processes. Okay. So any questions about the RMA? Yeah.
So can you do a put and accumulate on my own rank?
Yes. Yes. And in fact, there are times when you want to do that because otherwise, so for example, if you wanted to do exclusive access, the way to ensure that, and in fact, if you do an MPI win lock on your own process, that will allow you to use not just the MPI routines, but the regular load and store routines to access the window. And as a result, only in that case does MPI require the MPI win lock routine to block until it can get, on exclusive access, to block until you can access it. Because as soon as it returns, you could use just the loads and stores, and MPI doesn't know what's going on. So it has to block there. In other cases, it can do all sorts of things to optimize the communication. There was another, yes? Okay.
Can one process have multiple locks to different ranks?
I'm trying to remember. There's also, actually, there's a lock all that was added in MPI3. And so that, in most cases, that's the appropriate approach. So do a lock all, perform the operations, use the flush routines to complete them as opposed to the unlock.
That can be shared as well?
That can be, yeah. Other questions? Okay, so I wanted to say just a teeny bit about the memory model. The standard talks a lot about an abstraction, which is you've got private memory, which is known only to your process, and public memory, which is exposed to other processes. And when this was designed, the idea was that that public memory might actually be separate hardware, other memory chips in the network controller. And there would be an operation that would copy that data back into the process's address space. And there would even be things to do so that you could figure out what you needed to copy and so forth. And in fact, that kind of looks a lot like what you saw for the GPU memory models that are now being enabled, where stuff sort of gets automatically copied from one place to the other. And so it's not such an unusual model, and it might even come back. But right now, most MPI implementations are in systems where there is memory there's essentially one block of memory that is it's cache coherent among the different threads, and there's no separate memory in the network. And so in that case, in MPI3, this is called the unified memory model, as opposed to the separate model where there might be separate things. And a lot of what's described in the standard talks about how do you make sure that the public memory is synchronized with the private memory. Now, what's interesting is that that's is a interesting way to talk about how you ensure that changes you make to your memory are also visible to another process. So another comment that was made yesterday was that C and Fortran they're not parallel programming languages. They don't know about shared memory. And what the consequence of that is that you can write code that you think is right that uses shared memory, that the compiler will look at and say, I know exactly what's going on, and rearrange all sorts of things because it makes the code faster. However, in a shared memory context, it has now made the code, well, I can't say wrong, because in fact, what the compiler did was correct for the language, but it's not doing what you think it's doing. And you are now not going to get the result that you want. So classic example, in fact, I have seen this in very important science applications. It's okay, I'm on a SMP node. I'm not going to use this MPI stuff to move data. I'm just going to copy the halo data into the other target process, and then I'm going to have a flag bit or a word someplace, and I'm going to turn that word to 1 when the data is copied, right? Does that sound reasonable? Right? I copy the data, then I indicate that the data has been copied. Right? The problem is that there's nothing that says in the language that those store operations happen in that order. And not all hardware, for example, may look at that stream of addresses and say, that's really inconvenient. This last one here, I could do that now. And it goes ahead and does that now. And then the other ones happen. And this is like the worst case for a buggy code, because what's happening is your time stepping code sees that the flag has been set and starts running off and computing. Well, what data is it getting? It's getting the last time steps data. Well, that's not so bad. It's only off by delta t, or maybe delta t squared or something. It's off by a little bit because it's the old data, which means that what you're computing is a little bit wrong. Right? And that's why that's the worst possible case, because you'll never notice that it's a little bit wrong, but it's a little bit wrong. And so you need some way to make sure that everybody agrees on when data is accessible. And so in shared memory terms, you often have to insert a memory fence, which is a thing that says, do not proceed until all the memory operations that were issued before this point have completed. And you're sort of wondering, well, how do I do that in C and Fortran? Well, you don't. There's no way to express that in Fortran, and except for C11 and some little aspects of it. Actually, there's no way to express it in C11 for processes. There is a way to express it for threads. You just can't do it. In MPI, in that memory model, we sort of dual purpose some of the routines to say, for example, there's now a win sync, which essentially says, make those public and private copies the same. It has the effect of complete all of your memory operations before you go on. And so if you do the stores of the halo and then a sync and then set the flag, that will behave correctly. If you just think that because I wrote a store, 2 stores, one after the other, that they're going to happen in that order, that's not true. So bearing in mind that the shared memory programming model and that memory model, you have to be very careful about what you assume is going to happen, because the programming language has tremendous flexibility to reorder statements as long as in a single-threaded, non-shared memory case, they would compute the same thing. And as the compilers get pushed to be more and more effective, there's more and more opportunities for you to get very hard-to-find bugs that come up often by either, if you're lucky, it's some sort of shared memory you were doing with your data structures and your pointers, which means you'll occasionally get segmentation violations. But if you're unlucky, it's the case I just described, where you're just getting slightly less accurate computations. Okay. Any other? Yes.
Taking the same thing now to MPI, how do I actually make sure that all my sends and receives are actually performed to the end before I proceed with my program?
Well, with sends and
it is a function call, so it could say, okay,
if process A is sending to process B, the messages have to be delivered in order. So if I send them with the same tags from the same communicator, the implementation is required to make sure that they arrive in the same order. And so that's part of the specification. So unlike what the language says, which is that there's no sort of temporal ordering of the stores in the language, the MPI standard does have an ordering for the sends and receives.
But what does keep my compiler from rearranging accesses to the
For the most part, it's because it doesn't know what goes on in the routines, and they're not considered pure. So it doesn't know that it can, even in the single-threaded case, it's not safe to do the exchange. If you look at the MPI-2 standard or the MPI-3 standard, there's an entire section on issues with Fortran, which reflect the fact, in C, since most of these routines take pointers, the compiler is basically, it's hopeless. Since you've created pointers, a routine that the compiler can't look into could be doing basically anything. And so the compiler can't do much to change them. In Fortran, that's not really true because you can't take pointers of random objects, and there's a lot of restrictions on aliasing. And so there are pages of things that can go wrong with highly optimizing Fortran compilers and workarounds to try to fix that. It was particularly in MPI-2. MPI-3, there was a lot of interaction with the Fortran Standards Committee to try to address some of these issues, and they were maybe 90% successful. So there are things that you can now say about functions and routines that tell the compiler that it can't do some of these transformations. But there are still a few places where it can be tricky, particularly if your Fortran compiler isn't actually ahead of the current standard. So I'm not sure that's the answer you wanted to hear. But again, in C, the reason that you can program in threads in C is the same sort of thing, is that pretty much the compiler just doesn't have enough information to deal with the routines. In a few places in C where it might want to do that, C compilers often know about the thread routines so that they will know not to do that stuff with them.